So in this video, I'm going to run through the questions that come up in quiz 9. Main focus are these bond energy calculations. So in the question, you're going to be given a reaction and you're going to be given a table that has a list of bonds and then the energy associated with those bonds. And you're asked to calculate the energy change. To do that, you need to look at the reaction in two halves. You need to look at everything on the left-hand side of the arrow. They're the bonds that need to be broken. And then you need to look at what's on the right-hand side of the arrow. They're the bonds that need to be formed. So if we have a look here, you've got a list of all the bonds that you need. So the first bond here is CH. Do I have a CH bond that needs to be broken? The answer is yes, I do. How many of those CH bonds do I have? I've got 1, 2, 3, 4. I've got 4 CH bonds. So I'm going to write down CH times 4. The energy required to break a CH bond is 435. So I'm going to write 435, then I'm going to times it by 4 because I've got 4 of those bonds to break. The next bond on my table is O double bond O. Do I have an O double bond O on the left hand side? Yes, I do. I've got one here and I've got another O double bond O there. So I'm going to write that down. I've got O double bond O and I've got 2 of them. So I'm going to times it by 2. I've got 496 is the energy required to break an O double bond O, and I've got 2 of them. Then I look on the right hand side, what bonds am I forming? Next bond on my table, C double bond O. Do I have that on the right hand side? Yes, I do. I've got C double bond O there, okay, but I also have it going that way. So O double bond C and C double bond O, it's the same thing. So I've got 2 of those bonds in total. And then I've got an OH bond. Do I have that? Yes, I do. It's here on the right hand side. So they've written as HO. And then again, when I'm counting this, I've got 1, 2, but then 3, 4. HO is the same as OH. So I've got 4 of those bonds in total with a hydrogen bonded to an oxygen. And then, sorry, if I look at the values for the C double bond O, I've got 805 and I'm timesing it by 2. And for the OH bond, I've got 463 and I'm timesing it by 4. And then all I need to do is add up the total amount of energy required to break bonds on the left and add up the total amount of energy released when bonds are formed on the right. And when I do that, I get this. Okay, so this is the energy required. You need energy to break bonds, and this is the energy released. Energy is released when bonds are formed. And to calculate the total energy change, it's the energy required minus the energy released. So it's always the left-hand side minus the right-hand side, and you end up with an answer of minus 730. And the fact that it's a minus number tells you the reaction is exothermic. And that means that more energy is released than is required. So overall energy is released into the surroundings, and the surroundings are going to get hotter. If we look at the next question, it's similar, okay, but this time they haven't actually drawn the molecules for you, so it's slightly harder. So they've given you the equation, hydrogen reacts with fluorine. They're asking you again to calculate the energy change. They've given you all the bonds, but they haven't drawn what the molecules look like, okay, so that's what you're going to have to do first in order to be able to see what's been broken and what's being formed. So the first thing I've got here is H2, so that's 2 hydrogens joined together. So I'm going to draw 2 hydrogen atoms. Now you might not know what type of bond to put between the 2 hydrogen atoms, but if you look at the bonds that they've given you, the only bond they give you is a single bond, therefore it must be a single bond. Okay, it can't be H double bond H, or they would have given you that as an option. The next thing I've got is F2, which is going to be 2 fluorines joined together. Again, you might be wondering what type of bonds to put between the 2 fluorine atoms, but the only type of bond they've given you is a single bond, therefore it must be a single bond. So that's H2 and that's F2. And then on the other side of the arrow, I've got HF. So it's a hydrogen and a fluorine. And again, if I look at my table, I can see that I've got a single bond between hydrogen and fluorine. It's not a double bond, so I fill that in. But the difference here is that I've got a big 2 in front of the HF. And that means I've got 2 separate HFs. They are not bonded together, they are just totally separate HFs. And if you go back and you do another check, okay, fluorine is in group 7. It wants to gain 1 electron to have an outer shell. full outer shell, so therefore it forms one bond. So fluorine is always forming one bond because it wants to gain one electron to have a full outer shell, and then hydrogen's only got one electron, so its outer shell is the first shell. The first shell only holds 2 electrons, so hydrogen just needs one more electron for a full outer shell. So again, hydrogen just forms one bond. So what I've drawn here makes sense. Now that I've got it all drawn out, it's going to be easier to see what's been broken and what's been formed. So if I look at what I've got on the left hand side of my arrow, I've got a HH bond that needs to be broken. So I'm going to write down HH. I've only got one of them, and the value to break a H bond is 436. I've also got a fluorine bonded to a fluorine. Again, I've only got one of them, and the value to break a fluorine-fluorine bond is 158. Okay, so that tells you a fluorine-fluorine bond is weaker than a hydrogen-hydrogen bond. Less energy is required to break it. And then if I look at what I'm forming on the right-hand side, I'm forming a HF bond. Because I'm forming 2 HFs, I do need to form 2 separate HF bonds. So that value I'm going to times by 2. So it's going to be 562 times 2. And again, I need to add up all of those values. And I work out that the total amount of energy required to break bonds is 594. The total amount of energy released when bonds are formed is 1124. To calculate the energy change, it's what's on the left minus what's on the right. And again, I end up with a negative number, saying me again that this is an exothermic reaction. Got one more of this question type to do, and again they haven't drawn the molecules for you, so they've given you 2H2 and O2 goes to 2H2O. So again, I'm going to start by drawing this out. So I've got H2, which is 2 hydrogen atoms bonded together. Again, if I look at my table, I can see it's a single bond between 2 hydrogen atoms, and again I've got a big 2 in front of the H2, which means I need to draw this twice, 2 separate H2 molecules. The next thing I've got is O2, which is 2 oxygens joined together. If I look at my table, I can see that there is a double bond between the oxygens. There's no big number in front of O2, so I've just got one of them. And on the other side of my arrow, I've got H2O. So if I'm drawing H2O, the atom that's by itself always goes in the center. So I've got 2 hydrogens, only 1 oxygen. So I put the oxygen in the center. I'm going to have a hydrogen on the left, a hydrogen on the right. And again, to see what type of bond exists between them, I look at my table and I see I've got an OH single bond. So that's going to be there and that's going to be there. And again, I've got a big 2 in front of H2O, which means I need to draw this molecule twice. So I draw exactly the same thing again. And if I do a quick check, okay, oxygen's in group 6, it needs 2 electrons to get a full outer shell, so oxygen has to form 2 bonds. This oxygen here is forming 2 bonds, this oxygen here forms 2 bonds, this oxygen over here is forming 2 bonds, 1 to this hydrogen, 1 to this hydrogen, and the same down here. And as we saw before, hydrogen only wants to gain 1 electron, so it only forms 1 bond. So when I've got this all drawn out, I need to look and see what bonds I am breaking. So on the left hand side I have a HH bond that I have to break, and there are 2 of them, one there, so I've got 2 HH bonds to break. That's 435 then times 2. The next thing I've got to break is this O double bond O. So I write down O double bond O. I've only got 1 of those to break, so it's going to be 500. Bonds formed, I've got this HO bond that I'm going to need to break. So HO is the same as OH, they're all the same thing, and you can see I've got 1, 2, 3, 4 of them, where an oxygen is just bonded to a hydrogen, so I've got 4 of them to break, so it's going to be 460 times 4. Again, I add all that up, I subtract what I get on the left, so I subtract minus 1840 from 1370, and again I'm getting a negative answer. Again, this reaction is exothermic. So those questions are always worth 4 marks. If you do make a mistake at the start, you will get error carry forward, so make sure you do have a go, lay it out this way, keep your work nice and clear, and if you make a mistake I should be able to spot what you've done wrong and be able to give you the error carry forward marks. The next few questions just relate to concentration. These are really straightforward, okay? It gives you the unit in the question, grams per decimeters cubed, and that actually gives you the formula. Whatever you've got in grams, you need to divide by whatever you've got in decimeters cubed. In the question, I've got something in grams, so it's going to be 28.4 grams divided by whatever I've got in decimeters cubed. But if you go back up and search for the other number, you'll see the other number is actually in centimeters cubed, not decimeters cubed. So you're going to have to do a unit conversion. And to go from centimeters cubed to decimeters cubed, you just divide by 1000. So I'm going to do 250 divided by 1000. Now I've got a number in decimeters cubed. I plug that in here and do 28.4 divided by 0.250. Now it asks for my answer to 3 significant figures. 250. So initially when I do it on my calculator, I get 113.6, but you're asked for 3 significant figures. So I'm going to round that 3 up to a 4, and my answer is going to be 114. Next question is the same, okay? Unit in grams per decimeters cubed. It's whatever you've got in grams divided by whatever you've got in decimeters cubed. And in this case, they actually even give you that formula there. So I've got something in grams, 9.25 grams. I don't have anything in decimeters cubed. Again, it's centimeters cubed. So again, I'll need to divide that number by 1000 first. I get 0.2. So it's this divided by 0.2. And it's 9.25 divided by 0.2, and I get 46.25. Now in this case, they don't specify the number of significant figures, which is why it's worth 2 marks and not 3. Next question again, same thing, grams per decimeters cubed. Whatever you've got in grams, which is 3.14, divided by whatever you've got in decimeters cubed. Again, I don't have anything in decimeters cubed, it's in centimeters cubed. I divide by 1000, plug that in, and I get 3.14 divided by 0.25, and I get 12.56. Again, I'm not told about the number of significant figures, so I can leave it as it is. Okay, so they're all done exactly the same. Last little type of calculation, calculate the percentage by mass of chlorine in phosphorus oxychloride. What you need to do here is you need to get the formula mass of the full molecule. So the full molecule is POCl3, and to get the formula mass you need to be able to read the formula. I've got 1 phosphorus. Phosphorus has a mass of 31. I've got 1 oxygen. Oxygen has a mass of 16, but because it's Cl3, I've got 3 chlorines. Chlorine has a mass of 35.5, and I've got 3 of them, so I'm going to need 35.5 times 3. So I add all that up, and I get 153.5. So that's the total formula mass of POCl3, but they want to know how much of that 153.5 is because of chlorine. Well, chlorine has a mass of 35.5, and there are 3 of them, so I do 35.5 times 3. So in total, chlorine accounts for 106.5 out of the total 153.5. They want this as a percentage, so I have to times this by 100, and I get 69.38%. Next one up here is the same thing. Calculate the percentage by mass of copper in copper sulfate. This time it's a little bit easier. They give you the formula mass of copper sulfate straight away. And you've only got 1 copper in copper sulfate, so it's going to be 63.5, the mass of copper, over the mass of the whole thing, copper sulfate. Again, as a percentage means I need to times it by 100. 63.5, 159.5, and I get 39.812. But they says give your answer to the nearest whole number, which means I'm going to need to round this right up and give my answer as 40%. Last one here, exact same thing, the percentage of magnesium in magnesium carbonate. So I'm going to need to work out the formula mass of the whole thing, the magnesium carbonate. So I've got 1 magnesium. Magnesium has a mass of 24. I've got 1 carbon. Carbon has a mass of 12. And I've got 3 oxygens. Each oxygen has a mass of 16. So if I work that out, I get a total of 84. But how much of that 84 is because of the magnesium? There's only one magnesium. It's got a mass of 24. To get it as a percentage, it's 24 over the total, which is 84, and then I'm timesing it by 100, and I'm getting 28.57, and again, they haven't specified significant figures, so I don't need to worry about that.